Hey, also here I'm going to review for the hypothesis test for proportions test. Very similar to means, except a little bit different in the way that we make some of our calculations based on the information that we have. Uh, the structure, the skeleton, the process is the same. We need to establish that we have met some conditions. We need to make sure that our sample that we are looking at was obtained randomly. And so here we have randomly selected 200 people. And we are measuring the weights of these people and these young people, 2 to 19 years old, and deciding if they are be considered obese or not. And so uh, the weights of one of these 200 children should not really influence the weight of another of these 200 children. So we would say that the weights are independent. When we did hypothesis tests for means, we needed to make sure that our sample size was large enough. And so we were looking for a sample that was at least 30, so 30 or more. And that would allow us to use a normal model appropriately. Here we need to establish that our sample size is large enough, but we need to be a little bit more specific than that. We need to make sure that we have a large enough number of successes, because in this case, people are either going to be considered obese or not. And in this case, a success is considered a child that is obese. That might sound confusing, but that's just the way it's set up here. We need to make sure that we have enough successes in our sample and enough failures in our sample, children in this case that are not obese, in order to use a normal model and use it effectively. So that looks like this. We're calculating n times p. That is our sample size times our probability of success. And that needs to be greater than or equal to 10. N times q, our sample size n times q, our probability of failure. That needs to be greater than or equal to 10. So in our sample, we need at least 10 successes and 10 failures for this to be meaningful enough to use our normal distribution to make some calculations. And so it's not a bad idea to kind of document what you have. So we have sampled 200 people. That's N. We are believing that 17% of young people are obese. That is our P, 17% or 0.17. Q is 1 minus P. So if 17% of children are considered obese, then that means 83% or 0.83 are considered not obese. So these two decimals need to add up to 1, just like probability needs to add up to 1 or 100%. So to make these calculations, which we should actually do, I'm going to do my 200 times P. And when I do that, I get 34. And then I'm going to do my 200 times Q and get 166. Much like 0.17 and 0.83 should add to 1, 34 and 166 should add to 200 because I have 200 children sampled. And so my 34 that I would predict to be obese should add up to 200 with my 166 that I would predict to not be obese. So this is what we would predict if 17% of young people really are obese. And that leads us into our hypotheses, where our null hypothesis, the thing we're assuming is true until shown otherwise, is that our population proportion is equal to 0.17. And in this problem, we want to know if there's enough evidence to reject the claim. We're not really asked if it's greater than or less than. So when we are writing our alternative hypothesis, we're going to change that equals to a not equals. Just because we haven't established that we think that the proportion is greater, or we haven't thought that the proportion is less. We just want to know if it's different. And so that's a not equals to alternative, which means when we are calculating, we are going to have a two-tailed test. So when I am setting up my little sketch for my normal model and I'm putting 0.17 in the middle, because that's what we believe is true, I need to calculate p hat, my actual sample proportion. So when I sampled these 200 kids and I weighed them and decided if they are considered obese or not, we had 42 who were considered obese out of 200. So 21% of my sample. That's going to be over here somewhere. And so I would color in that tail. And because it's a not equals to, I'm coloring in both tails. So I'm going to make a calculation on Desmos that's going to give me this area here on the right. And then I'm going to have to multiply it by 2 so I can account for both tails, because I'm not specifically worried about greater than or less than. I'm just wanting to know, is the proportion different? So it could be either. So I have a normal distribution. 0.17 is my mean. That's the thing that's in the middle. To find the standard error, I do the square root of p times q over n. So in this case, the square root of 0.17 times 0.83 divided by 200. I'm finding this area right here, right now. So when I'm telling it my minimum in Desmos, my minimum for that area is 0.21 because it's on the left. And my maximum is infinity because that thing goes to the right forever. And so when I put this into Desmos just the way I wrote it, I'm going to get 0.066. I probably rounded that. And then because it's a two-tailed test, I need to double that to get my final p-value, which is 0.13. So this is my p-value. This is the probability that if I took a sample of 200 kids and got a proportion that is 21%, this is the probability that happens if the true proportion of kids who are obese is 17% still. So a 13% chance that my sample turns out this way if the true proportion of kids that are obese is 17%. 13% sounds low, but it's actually pretty high. If I added 13% to your grade right now, you'd be pretty pumped up about that. So it's not nothing, it's not insignificant. Just like with the means, though, we are going to compare our p-value and our alpha value. And so in this case, up in the problem, you can see that the alpha was 0.05. Our p-value, as just discussed, is 0.13. When the p-value is small, when it is smaller than alpha, then we reject the null. In this case, the p-value is larger. And so we are going to fail to reject the null hypothesis. And as a reminder, we will never say that we accept the null hypothesis. We are not proving that it's 17%. We just don't have enough evidence to say that it is not 17%. So we just have to fail to reject it. And we would say there is not enough evidence to show that it's not 70 or 17%. So we will write this up just like we did with means. And I'm actually going to go down here into the second space because I've run out of space. So we always establish what is our p-value. So our p-value is 0.13. We establish what alpha did we compare that to, 0.05. Because I've failed to reject, I'm going to say there is not enough evidence. And these are all the things I'm looking for when you're showing me that you know how to do this. I'm looking for that you've identified P and alpha. I'm looking that you told me whether or not there was enough evidence. And then I'm looking that you told me about the context of the problem. Evidence of what? So evidence that the proportion of obese children is different. That's what that not equals to means. Different than 17%. So we did not have enough evidence to show because we failed to reject a null hypothesis. So we are moving on here, still assuming that 17% is a proportion, but we have not proven it. We just don't have enough evidence to show that it's not true. So very similar to a hypothesis test for means, except for some of the calculations. So the order in which you do things is the same. The way you write up your interpretation at the end is the same. The way that you decide to reject or fail to reject is the same. If I have one or two tails, calculating the p-value is the same. The big place where we have differences here is this piece that we have to enter into the calculator. That standard error is different when we have proportions, as well as this piece where we are deciding if our sample size is large enough. So when we have means, it just needs to be equal to or greater than 30. When we have proportions, we have to do this NP and NQ calculation and make sure these two numbers are bigger than 10. And you could put a little check mark there, like I did on the last one, to say, hey, we've met this condition. So make sure that if you do still have questions after watching this, that you send me an email or get in touch with me as soon as possible to ask for some help. Maybe practice one step at a time if you haven't done all the practice. You should definitely do all the practice so that you can keep trying and keep reinforcing how to do this. Take your time on this and good luck.